Hi everybody, welcome to section 8.2, which is another confidence interval for the mean, but this time we're assuming that sigma is unknown, so we don't know the population standard deviation. So when that's the case, we could just use the sample standard deviation to estimate the population standard deviation. So we're estimating sigma by using S. So using the second parameter, using the sample standard deviation to help estimate the sample mean, increases the amount of variability in the estimate. So we need a wider confidence interval. To get the wider confidence interval, we have to have a different distribution. So we can't use the Z distribution anymore. We have to use the T. And I could call this up here the T distribution, or the T interval. Okay, so the other one was the Z interval, this one's the T. So the T distribution is basically the same shape as the Z. It's just wider. But it's based on something called degrees of freedom. And you don't need to know what a degree of freedom is. You just need to know that it's n minus 1. So the sample size minus 1. And as the degrees of freedom get larger, the T distribution gets closer and closer to the Z distribution. So if you've got a small degrees of freedom, it's going to be like this green one here where it's wide. If you get a larger degrees of freedom, like up closer to 30, it starts to look where it's pretty close. And all along we've been saying that kind of 30 is considered to be a large sample size. And this is why. Because where you get to about 30 degrees of freedom, or 29 or so, the T distribution starts getting so close to the Z that they're practically equal. They're not exactly equal, but they're pretty close. So that's where the 30 comes from. By the way, I want to tell you, I don't want you to leave this course thinking that 30 is the magic sample size for what you need for, the whole rest of your life. 30 is not a magic sample size. For most populations, 30 is a very small sample. But we say it's a large sample just because of this. Just because at 30, we can say that T and Z are pretty close to each other. So the formula for the confidence interval for the mean based on the T distribution is exactly the same as based on the Z distribution, except for two things. Instead of sigma up here, we have S, and instead of Z here, we have T. To find values from the T distribution, it's very easy. All you have to do is use this Excel function t.inv.2t. Okay, and you can hit the FX button to get some help with it. Oh, where'd it go? So you need to put in two values here, the probability and the degrees of freedom. The probability is going to be 1 minus your confidence level. So for this first one here, for a 95% confidence interval with n equals 50, our probability is going to be 0.05, and our degrees of freedom are going to be 49. And so we get this value 2.0096. Okay? So our probability is 0.05 because it's 1 minus this confidence level. And our degrees of freedom is the sample size minus 1. Okay, so that tells us that T is 2.0096. Now for a 99% confidence interval with n equals 15, our probability is going to be 0.01. This is 1 minus the 0.99. Our degrees of freedom are going to be 14. And so probability 0.01, degrees of freedom 14. This gives us 2.9768. All right, so that's how you find those values of T. Now let's do an example. We took a sample of 25 breakfast cereals and figured out the mean calories per serving was 110, and it had a standard deviation of 17. And we know this is from the sample because the way this is phrased, this said the sample has a mean and the standard deviation. So that means that this is S, and this is X bar, this is N, and they want a 90% confidence interval. So to get our value of T, our tail area, our probability, is going to be 0.10 because 1 minus 90%. And our degrees of freedom is 25 because it's the sample size minus 1 gives us 24. Therefore, based on this, 0.10 and 24. And again, this function we're using is t.inv.2t. It's 1.7109. So now to get the rest of the problem, so we just plug in X bar was 110 plus or minus 1.7109, and we're writing that down, although you're going to just use it directly in Excel, times S, which is 17, over the square root of the sample size, which is 25. So that's 110 plus or minus. So that's going to be our 1.7109. And again, we're referring to it directly here, times 17 over the square root of 25. So we get 5.817. And if we write that in interval form, we'll write the lowest one first, and then we'll write the upper one, and so our interval then is 104.183 up to 115.817. And down here we've got our interpretation. We are 90% confident that the mean calories per serving for all breakfast cereals is between these two calorie counts. Okay, and I rounded that there. I probably shouldn't have. Now, how would this look different if what you had was an actual list of data rather than summary statistics? Well, it would be exactly the same, except that you would need to calculate the summary statistics. So if you had, just a data set, a whole list of data, you'd just use average to calculate the mean, and you'd use stdev.s to calculate the sample standard deviation. And then you just plug it in there, and you'd be good from there at that point. There is a shortcut that I will allow you to use as long as you can do it both ways. This gives you, this confidence.t function gives you the margin of error. It doesn't save you a whole lot of time, but it might save you some. So if we want to do this problem using this, confidence.t, and you see where here you have to input alpha. That means 1 minus the confidence level. So 90% would be 0.1, this is 1 minus 0.9, and then comma, your standard deviation, which in this case was given in the problem to be 17, and the sample size is 25. That gives you your margin of error in a slightly faster way. But the reason I'm making you know how to do it both ways is I want you to see how similar the Z and the T are. And I want you to know, why we're using that distribution. One more thing in this section, and then we'll be done. You need to know which formula to use when you read a given problem. That part's really important. So for now, I know you've got one section and then the other, and so it's pretty obvious. But later on, on a test or something, you might not know. So here's the difference. You're going to use the Z interval, what we did in section 8.1, when the population standard deviation is known. And here are two ways you might see that written. They might say the population standard deviation is, or is known to be, or they might say sigma equals. You use the T interval formula when the population standard deviation is not known. And you might see that in these three ways. If they say, here's the sample standard deviation, if they say S equals, or if what you have is not summary statistics but a list of data, and you have to compute the standard deviation. All right, so this, whenever they give you a list of data, it's going to be a sample rather than a population. So this is going to be a sample standard deviation here. All right, so this is kind of a key here for determining which formula to use. And that's it for this section. And, as always, please, if you have any questions, let me know.